No, thank you for joining, Krassi. I really appreciate it. We're online. Thank you.
Thank you, Omar. Good morning, good afternoon, and good evening to everyone. Welcome to Django, and I wanted to extend my appreciation thanks to the Red Team Village and Texas Cyber. Today, we are going to be looking at what you need to know in order to be effective mitigating some denial of service attacks, but more importantly, to be able to interact with other teams and companies that you will be able to use to help you with this. Just a brief introduction. I am currently a graduate student at Purdue University. I am focusing on cybersecurity, mostly in the space of counterintelligence techniques and influence operations. But I used to do DDoS mitigation for many years, including as a part of my previous job right before I came to school. Currently, I also work for the CyberTap program, which is a program within Purdue that provides help to local businesses within the state of Indiana to do that without any cost for those businesses. So that's pretty much it. If you need to contact me, at the bottom of the screen are my 2 emails. You can see more about me on my LinkedIn profile. And that's pretty much it. Now, one thing I would like to also ask you is if you have any questions, please send them to the Track 3 Briefings channel. I will be monitoring this channel, and I will try to either directly answer the question or incorporate the answer in the current narrative of the slide that I'm covering. So don't be shy, ask questions. This always goes better because also when I see the questions, I can tune and kind of figure out where the audience is. I obviously do not have the visual cues to see how people are responding, so that helps me as well. So without further ado, what is DDoS? Any brave souls? Let's see who can use Discord. All right, it looks everybody is very shy. So in general, this is a resource exhaustion. Many people think about denial of service as an overloaded pipe, which in some cases is correct, but it doesn't need to be that way. In many attacks, you may actually see decrease in traffic on a particular network connection as a result of the denial of service attack. So in general, this is going to be a resource exhaustion, which is going to in turn lead to lack of availability. Now, this is also very interesting to mention because this is very similar to having a small website being advertised or highlighted on a much larger media platform, and then suddenly this website gets so much traffic that they're unable to serve that traffic. So it will kind of feel the same way to that small website being overwhelmed by the incoming traffic. Now, having said that, this also may appear like an outage. And again, this is kind of interesting to look at because many people perceive DDoS as this magic thing that happens and nobody can do anything about it. But we already have ways to deal with a lot of traffic with an outage and so on. So we'll kind of look at how to apply those in this space. So from security point of view, denial of service would be what? Any guesses? Okay, it's distributed. And what is security? From security point of view, how would you classify a denial of service attack? Okay, let's really go and look into the CIA triad. So what do we have there? We have confidentiality, integrity, and availability. So from security point of view, we are going to be breaching which one of the 3? It would be availability. So DDoS is a security event, though it is not the type of security event we're used to talking about. Many people were talking about breaches, data leaks, and so on. However, in this case, we have decreased availability. Now, from operations point of view, this will be an outage. And as I mentioned a few minutes ago, it is very important to realize that because operations people for many, many years have figured out how to deal with outages, build redundancy, distribute traffic, and so on. So it's very important as a security person to be able to interface with your operations team and be able to use whatever resources they can offer when you're dealing with this type of event. From business point of view, this is financial loss. And why is that important? Well, if you want to prepare your company to deal with denial of service attacks, you will need to have a budget. And how do you justify that budget to your management? Well, you have to know how much money the company will lose when an adverse event occurs. So the first and most important question you need to ask your management is, how much money are we going to lose if the website is down for 1 hour, or for 1 minute, or for 1 day, depending on your type of industry? And hopefully they'll be able to give you this information, but unfortunately, in most of my experience, people have not been able to provide that information. So the first task there is to work with executive management to see how much they value the website. What value do they assign for 1 hour of outage? Now, once you have this information, you need to look at the company profile and the probability of the company being attacked, and then you can more easily justify budget to invest in denial of service mitigation. Excellent. I'm just catching up with the channel. Okay, so really briefly, just for semantics, what is the difference between DDoS and denial of service and just denial of service? So distributed versus not distributed. All right, when we have just denial of service, we have an attacker, and there is only one source of that traffic that is hitting the target. Many years ago, SimFood was very popular. Now, funnily enough, SimFood is still popular, but it is not as effective as some of the other attack types. But many years ago, you would only have one single machine over a modem, and it would be able to deny of service a couple of servers. Here we're talking like 25 years ago. Nowadays, things are not as trivial, but if we look into this picture, we're going to see the next generation. So we have a distributed attack where we have an attacker that is controlling a command and control server, and now the command and control server will issue commands to bots, and then the traffic is going to be coming from many different sources. And just a quick note here, I'm realizing that maybe the video streaming is delaying the delivery of video. So I will try to ask the questions a little bit early and provide a little bit more time for the answers, because I'm seeing your answers coming like 10 seconds after I have passed a topic. So just noting this. So yeah, here you have multiple sources of the attack that are going towards the target. Well, here we have a botnet, but we can also achieve the exact same result using reflective attacks, where we have number of reflectors, and all of those reflectors are sending traffic towards the victim. So this again is distributed denial of service attack. Any questions so far? Okay, so why are we seeing so much DDoS lately? Is it just marketing, or is it objective? Well, there's a couple of things that are going on right now. First, we have Moore's law. And according to the Moore's law, we're going to have 2 times more transistors on the same square footage of a die, or square, centimeter square and so on a die every 18 months. Well, bandwidth doesn't grow as fast, but approximately every 2 years, all of the bandwidth or the connections between different points doubles, which in turn means that we'll be able to carry more traffic towards a victim. One of the things that is not understood very well is that if somebody has a large botnet and can generate a lot of traffic at the point of each of those drones, that doesn't mean that they will be successfully able to deliver all this traffic to the target. Think about a giant botnet within China that is trying to attack something in, let's say, Japan. Well, they have to go through to the Great China Firewall, which is going to be a limiting factor for that bandwidth. So no matter how big the botnet is, also the fabric that is going to deliver this attack is in play. So in a little bit less extreme, if you're trying to attack somebody let's say in Europe, and you have botnet in Europe, you obviously will probably be able to deliver most of that attack traffic to the victim. If it has to go through some transatlantic links, maybe that will shed off some of the traffic, because it will be dropped because it's overrunning some of the links. Or if you have, for example, a botnet that is focused in a particular home provider, those are very quickly going to exhaust the upload bandwidth for that provider. So the full scale of the attack is not going to be delivered to the target. It's going to be filtered at the close to the source. So by having more available bandwidth on the internet, this enables more of the attack traffic to be transported. This is why we're able to see what lot bigger attacks. Now, this also provides, as the internet is growing, there's more devices that can be exploited, and also those devices can send at higher bandwidth. So when somebody brags about a really big attack, this is not that important because those numbers will continue growing, and that's just the way the world is. However, what's important is what percentage of the bandwidth of the target or particular resource that is being exploited has been consumed, and what is their overhead that they can continue operating in. Now, reflectors is one of the other factors. So about 5-6 years ago, little after the 2013 attacks against the US financial industry, reflectors became very popular. So different attacks using reflectors were introduced. For now, I'm just going to mention that UDP is extensively used in those cases and some of the properties of UDP, but those can also go over TCP, and we'll go in more details a little bit later. The next few are IoT devices, content management systems, the creation of so-called booters or stressors, and the access to information. So let's look in more details in those four. Home routers and IoT in general, just having a lot of those devices that some of them come with default usernames and passwords. Some of them have recursive DNS resolvers open on the internet interface. Also bugs in those devices. In some cases, they have network diagnostic tools that are accessible without username and password and can be used to send traffic by, let's say, sending large size ping packets and so on. So that's one of the challenges. In particular, attacks here are Mirai in 2016. Then we had a bunch of derivatives from Mirai. Actually, the author of Centauri got sentenced yesterday. No, on Thursday. On Thursday. So this was a long string of issues coming from embedded devices, and we have seen quite a lot of those. Now, compromised content management systems, those were actually very popular around 2013 when they were mostly used against some of the attacks against the financial industry. Those are still popular, but not as much as compromised embedded devices, or IoT as we call them nowadays. Yep. So booters and stressors, this is another interesting phenomenon because they are not bringing anything conceptually new from technical point of view. However, they lower the bar of using denial of service attacks. Those services came around, emerged around the gaming industry, the online gaming industry, where people would play a game and they would need to boot somebody off the game. For example, when they're doing a World of Warcraft raid or League of Legends and so on. Those are usually short interactions. They don't need the person to be offline for more than 3 to 5 minutes. And this is how those services have also shaped their offerings. The attacks usually are very short-term, 5-10 minutes maximum. They can range between 5 to 10 gigabits. In some cases, we have seen going up to 40 gig, but it's basically they are fairly low resource attack to execute, and they cause a lot of disruption because you can see how high they can go. Also, when they're attacking home modems, there are certain things around the oversubscription of home lines and so on, which causes a lot of problems. And because they are very, very cheap, it is very easy for people to pay $50 and launch as many attacks as they want to. Any questions so far? So I wanted to kind of look at the monetary side of, or the cost of reflection, and then we'll start going more technical things. So if in the past I wanted to execute an attack, I would need to have a command and control server, which I would probably, as an attacker, would probably buy with a stolen credit card, but I also have to preferably get it in a bulletproof location so that the data cannot easily be seized and so on. So that's one expense. Then, in order to run this attack, I would require a large network of drones that will be sending this traffic. So what does that mean? I would have to either pay for those, do something like pay per install. I think 2-3 years ago, when I was last doing research in this space, 1,000 hosts in the US would cost about $140 for pay per install. I pay somebody $140, they install 1,000 copies of my malicious software that can execute those attacks. And now here you can immediately see, if I can pay that money to have something installed on those people's machines, why would I be wasting my time with denial of service when I can be stealing credit cards, for example? But again, just kind of looking at the cost of executing attacks the old way, then the next thing is, I can have the attack. Now, also from legal point of view, actually, there's one thing I wanted to mention here is that for all of those machines that are compromised, this is a federal statute violation. And it is, I can be charged with that potentially. So I have also legal risk, which adds to the cost. This is a deterrent for the attackers. The other thing is having a centralized CNC is basically creating this dynamic where I can easily be wiretapped and data can also be collected. If somebody can get their hands on the CNC, they can get a lot of information about me and what attacks I was executing, and also what the targets were and so on. So there are a lot of downsides of using a botnet to execute denial of service attacks. Now, if we look at reflectors, we have another dynamic. Those machines that reflect the attacks are not compromised. They're just misconfigured, and they're not misconfigured by the attacker. They're misconfigured by the owner. So all the attacker does is they're sending some trigger traffic that is going to trigger a much bigger response going to the victim. I'm not saying this is legal, but there is far less footprint that the attacker is leaving, and there is far less traces of what they did. The other thing is that also they don't need to have a centralized control server. Now, in many cases, they may execute the attacks from a server that's in a co-location, but again, it's not a CNC server per se, and it can be moved very quickly. Now, the other thing that the attacker needs is a list of reflectors. Those go fairly cheap in the online forums, and also they're very easy to create. You can just start scanning the internet, see what systems are responding to those queries, and build the list yourself. Now, there's some other trickery around building those lists, but this is more on the offensive side, doesn't pertain to defense. So, questions so far? Okay, so just in a couple of words, the motivation of attackers is very, very wide range. And they range from script kiddies to people that do this professionally and are going after a particular goal, disrupting the availability of particular resource, maybe to conceal another operation or something along those lines. So the range of attackers is pretty wide. Motivation, same story, very wide. Could be anything. Anything could cause this, including somebody upsetting somebody else in high school, or somebody playing a game and making an inappropriate comment, or comment that is perceived as inappropriate by somebody, and they can launch an attack. So there's a bunch of motivations there. Now, I want to look a little bit more at the booters because they're the plague of modern DDoS society. This, as I mentioned earlier, started about 5 years ago. Most of the attacks that they're using are reflective attacks, just because it's easy to get those going. You don't have to have a large botnet. You don't have to infect machines. You don't have to be skilled, as a matter of fact. You can buy a kit for $50, $200, $500, and then in some cases free, and just install it on a VPS and then profit. As I mentioned, short, bursty, rudimentary scripts in many cases. Now, what do they do on the front end when they sell those attacks? This is what some of the panels look like. This is what the pricing models are like. You can see that they're, somewhat speculative. Who would buy VIP Ultimate, right? $1,000. I don't think so. Now, what's also interesting is that we have the same operator sometimes operate multiple front ends to the same infrastructure on the back. In one of the cases, this was just because the person had very bad service. So he basically was monetizing the capability multiple times. First, people go buy service from one of the places, then they get upset because it's not very high quality. Then they'll go to the other one, and because those were very low, like $15 to $20 to $50 a month, most people would not even complain and ask a refund, or even if they asked for a refund, they would not get. But this was a way to monetize this. The other reason for code use is just because those are kits that are just sold between criminals and or distributed between criminals, and this is why we see the same basically panel. You can see here those two just basically have different color schema. Questions? Now, one interesting thing about the booters while you're typing questions is a lot of the teenagers have the perception, or at least have justification, believing that this is not illegal, and that obviously is not the case, because we have seen many of them so far being put in jail. But I think it's also important to be able to spread this message and basically make sure that younger people understand that this is very illegal. The NCA ran an ad on hack forums for several months, and they did measure decrease in attacks just because of this awareness campaign that they were running. Also, the hack forums admin was cooperative, and they pinned the announcement that the NCA had put explaining that this is an illegal activity. And for the ones that don't know what NCA is the British equivalent for our FBI. Okay, so looking at the attacks, SymFlood. So what is the SymFlood exploiting? It is exploiting the so-called three-way handshake. And I think everybody here knows what a three-way handshake is, but I'm going to go over it very briefly just so that I can illustrate certain points. So the client will send a packet which will have the synchronization bit on, and this will be a signal for the server that this acknowledgement number here is not valid, just because there's nothing for this client to acknowledge. What's also interesting is that there is going to be this sequence number. Now, the sequence numbers are fairly large. I'm using small numbers just because we're human and don't deal very well with large numbers. Now, the server will store this sequence number and a bunch of other properties in this storage unit here, in this queue, and will then respond. Now, note, by definition, it's going to increase the acknowledgement number. Sorry, increase the sequence number by 1, and this is going to be the acknowledgement. So it's acknowledging the sequence number here. And then it's going to create its own random sequence number. Many years ago, those were not very random. If you remember the Kevin Mitnick exploit against Tsutomu Shimomura's machine, he used the fact that at the time the terminal was not generating random sequence numbers, so he was able to predict the range within which he had to send the following packet to make the machine believe that there was a three-way handshake established. So having said that, though, we have this sequence number, and it is key for our purposes, and we'll see why in a second. Now, the third packet to close the three-way handshake, obviously acknowledging this sequence number 550 here, 550 plus 1, and then the sequence number continues to be 101 plus 1 because there's no data we're sending. There's not, and so there's nothing we need to increase. If we were to send some data, this number here would increase. But remember, this thing here, 101, is something that the server is going to use to make sure that this packet and all the properties that are stored here, like source IP, destination IP, and TCP options, and so on, and the sequence number match. The sequence number obviously will be with 1 plus, but that's very easy to subtract. So what does the attacker do? The attacker will exploit this very storage unit here, when they send a lot of packets, this storage unit is going to be overloaded. And the moment it sends another packet out that is at the end of the queue, it's just not going to accept it. So basically, the attacker, all they need to do is send a bunch of packets. Now, why am I using random IP addresses here from the attacker side? Why am I not using the attacker's IP address or just a specific IP that may be somebody else? Okay, so if I was the defender and if I see the same IP address sending me all this malicious traffic, I can very easily drop this traffic. And that will be very easy to defend. This is why the attacker needs to use random numbers here so that the server side cannot distinguish which one is attack traffic versus legitimate traffic. Now, what are we going to do to defend this? Just a little bit details when the resets will be returned, but the thing is that we have a queue size, and this queue size in kernel 4.18 is 128 entries. Before that, it was up about 1K to 2K, but let's think about this. If I send a packet, which is actually, let's do the calculation on the next slide. This is where I have it broken down. So how much bandwidth do I need to keep one queue saturated? So first, let's use backlog size of 1,000. Here, I'm intentionally increasing it just to demonstrate how more vulnerable the servers actually are to this type of attack. Now, the backlog SYN receive timeout is 60 seconds. And since it's 60 seconds, I need to send 1,000 packets every 60 seconds to keep this queue full, right? What is the SYN packet size? So the smallest legal packet would basically be determined by the size of the frame. So you can only have 64-byte frame on Ethernet. You cannot have anything smaller than that, and that's for historical reasons from TINNET and the timing and collision detection and so on. But you have 64-byte frame, then you have 20 bytes inter-packet gap. So this is the timing between frames. And basically, you can say that one packet with SYN flag on will be 84 bytes. So if I want to send to saturate this server, all I need is to send 16 packets per second, which multiplied by 60 seconds basically will exceed this 1,000. Or this is 1.4K. In order to saturate one server that has 1,000 slots. And as I mentioned in the previous slide, the current kernel by default has only 128 slots. So let's think what will happen if I lower the timeout or increase the backlog. So if I lower the timeout, if I lower it to 30 seconds, that means automatically that my attacker will have to send 2.8 kilobits. Well, no problem, right? Still on GSM version 2, 2G, that's only a third of the bandwidth available to the 2G phone. Let's go down to 10 seconds. So this is 6 times this number. Again, still very little. This is the 9600 that the 2G modem without Edge or any extensions can do. Still very low. What if I go to 1 second? Then we increase this by 60 and we have suddenly 90K. Well, who cares, right? 90K is nothing modern day. So obviously, this is not going to help us much. Now, the other problem we have is that the moment we start going below 2 seconds, we're going to start dropping large amounts of legitimate traffic. The moment we go below 1 second or to 1 second, that means we're going to be losing a lot of legitimate clients. So this definitely is not a way for us to go and mitigate. Similar logic with the backlog. Doubling the backlog only requires the attacker to double this number, which again is not going to help us much because we'll run out of memory or the ability to scan that table efficiently before the attacker runs out of bandwidth on a home cable modem. Now, how would this attack look like on the receiving end? well, the receiving end is going to see a lot of sockets in SYN receive state. This is how they're going to know that they have a SYN FUD. And they will usually be on the same target port. Well, not usually, they will be on the same target port, which is being attacked. And they'll be coming from all kinds of foreign IP addresses. Here I'm simulating this in a virtual machine. That's why it's 120, it's a local host. Now, how do we mitigate this? So we obviously saw that obviously queue length and timeout is not helping us solve this problem. Well, there were certain things we needed to preserve in the packet, or the first packet that the client sends to the server, that go into this storage unit on the right side of the server, if you remember. So if we take those key elements like source IP, destination IP, source port, destination port, and select options, and then we also add a timestamp just so that we can protect ourselves from replay attacks, we can take this information and we can hash it and get this 24-bit hash. Remember how I was talking about the initial sequence numbers from the point of view of from the direction of server to client? Well, that's a 32-bit field. So we take this information and we stick it into this field and see what happens. So we have the first SYN packet, and then this is the hash. This will be the SYN cookie. The server is going to calculate this based on the source IP, destination port, and so on. And then it's going to use this number as its initial sequence number. Well, we know what's going to happen. This number is going to come back in the third packet increased by 1. Well, everybody can subtract 1 from that number. So if the server takes all of the properties that we looked at a second ago, like IP, source IP, destination IP, source port, destination port, it can calculate the exact same hash as it did for packet number 1 and compare it with this number. And if they match, that means that packet number 1 was actually sent. At this point, the server can just outright drop or not have to remember anything about packet number 1. Any questions on this? So basically, just to summarize this, by using a hash to preserve or attest that some information that is gathered from packet number 1 and stored here, we use a hash to attest that we have this information, or that the first packet really happened, by including this hash in the third packet. And if the server can calculate successfully and match those hashes, it has assurance that the first packet of the connection happened. Thus, it doesn't even need to remember anything regarding incoming connections. So this is how SYN cookies work. And just quickly, the only downside of SYN cookies is that the TCP options that are stored or that can be conveyed through this hashing mechanism are very limited. And this is why they are off until the machine needs to start using SYN cookies. So when this queue here starts to fill up, then the machine is going to enable SYN cookie processing. Before that, it's going to operate normally. And this is just to increase performance or when there is no attack. Okay. So no questions. That means either the video stream is completely broken and nothing is going through, or everybody's fallen asleep. Okay, so looking at amplification and reflection, we have a couple of terms that very often get commingled, and I just want to go over quickly the two of them. So reflection is when you use certain properties of the protocol, very specifically, those are mostly abused around UDP, to direct traffic to the victim by replacing the source IP address of packet like this. So I'm the attacker, and I have the reflector, and here I'm going to replace the source IP with the IP of the target. And whenever this traffic goes back, whatever this traffic is, it is going to basically hit the target. So this is reflection. Now, amplification is complementary, which basically is if I send a small query and I receive a large answer, this is what the amplification component is. Now, here a quick note, domains that have DNSSEC enabled are particularly how to say, they can create a very large answer. They're very prolific in in the answers that they provide. But don't hold this against DNSSEC just because if I'm the attacker to execute some of those attacks, I do not need to actually find one of those domains, and I'll cover this in just a second. I got sidetracked here, but basically the idea is that we have a packet that is going to give me much bigger response. So let's look at DNS. Long time ago, we had a limit of 512. Oh, thank you. You used to have 512 bytes response. So why was that? Many years ago, this was how DNS was designed. This is also the reason we only have 13 root servers, because in the original specification, once you were going to send this query to ask for the root servers, you're going to get everything lumped in this packet, but then they could only fit 13 IP addresses in this response. So just a piece of trivia there. So having said that, though, there's an extension called EDNS0, which allows for much larger answers. So this is how DNS can actually be used to return much larger answers than originally many years ago. And here I'm quickly kind of covering some of the amplifier types, and then I'm going to tie both of them together. So this is a publication of US CERT, and you can see the different amplification factors. Now, some of those are not, I would say, very accurate, but it gives a very, very good overview of the damage that can be caused. Like you see memcached, like when you start streaming data of a bucket, it can get really, really bad. Okay, so let's tie both of those together in an attack called DNS deflection. So we're going to do a dig, and what's going to happen is we're going to get this really big answer. We're sending the packet, but we replaced the source IP address with the one of our target. And then our target gets a really big packet. Now this could be a 4K, 8K, and more. Now, here is the note I wanted to make a little bit earlier. What's interesting here is that the Purdue name servers do not need to know anything about this attack happening. It is just the fact that this attacker is going to use a recursive DNS server which has cached the answer for this query, and they're going to return this answer. With the same success, the attacker can create their own domain, call it whatever they want, and they can stick whatever records they want to put in that domain just to make the answer bigger. So note that in DDoS, in reflected DNS attacks, whatever the domain is used, they have absolutely no clue what's happening, and they're usually just used because of the size of the answer. Now, in some cases, when you're investigating this, it may give you a hint who the attacker is and why they're using this, but that's kind of a rare thing. So one of the examples is ISC was attacked, it was probably, what, 7 years ago? And it was attacked by particular Russian criminals that were taken down, or a botnet that they had was taken down before, a little before that. So they used ISC as the domain just to kind of signal their discontent. But there's really not much to the actual name. It's all about the size of the response. Now, having said that, we have one query and one large response, which is not that bad. However, what the attackers would do, they're going to take a very large number of reflectors and they're going to start flooding them with queries, and then all of those are going to start flooding the target with responses. And that's how the attack works. Any questions so far on DNS deflection? I'm seeing somebody stepping, that's why I'm holding it for a second. Well, I guess they gave up. Okay, I will, so if you have questions, I can go back to the slides and also type those, basically go back and answer the question, even if I'm in the next section. Okay, so NTP reflection. A very similar situation, because it runs over UDP. Here, the difference in logistics is that we have basically the notion of those stratum servers, different stratum. So the lower the number is, the closer they're to more precise time, more accurate time. And then we have a workstation here. Now, what's going to happen is that historically, if you have an entire organization and many people querying this NTP server, if you want to take it down for maintenance, for example, it's going to be very helpful for you to know what IP addresses have been querying this server, just so that you know who is going to be without time for the duration of the maintenance. Now, to make this even easier for the administrator, instead of them having to log into the machine and look through the log files, they decided to create this command, which is an extension. It's a monlist is what's query it's called, but it's something else in NTP, that basically will query this list of IP addresses, and it's going to be returned to the admin. So you can see here how, if I was to be the bad guy, I can just use this information and make a request to get a list of those IP addresses and just substitute my IP address for the IP address of the victim, and then the answer is going to go to the victim. Now, here we only have 3 clients, mostly because I was too lazy to have more populated, but also because in reality, there will not be a very large number of machines that are going to be querying this NTP server, maybe 50 at, kind of the upper end. However, this buffer here is 600 entries. So the attacker can actually go and send some fake queries, pre-populate this, go up to 600 entries, and then from there, they can do the same with many machines and then send the query to many machines, which are going to deny of service the victim. So again, going back here, the attacker is going to substitute their source IP address for the one of the victim. The traffic is going to go to the victim, but also the attacker is going to prime those caches by sending a lot of fake queries to them, or queries from non-existent IP addresses, just to populate those so that they have higher reflection ratio. And then they're going to send many queries to different machines, which is going to deny service the attack. So this attack is fairly popular, but not as popular as DNS reflection. I would say DNS reflection is probably one of the most popular nowadays. There's also actually a variation of the SIM-FUD attack, where they're actually using using TCP and the SIM packet as a reflection. And you're going to say, well, but there's no amplification. Yes, technically there is no amplification in the SYN-ACK packet. However, the host that receives the packet will have to retry 3 to 5 times, depending on the stack of on the operating system. So there is still a little bit of amplification there. If you start sending SYN packets to a lot of machines on the internet, with the victim being with the victim IP being the source IP, then there still is going to be a lot of traffic coming back to that victim, multiplied 5 times. But then it's also going to conceal your IP address, so it's not going to be visible where the attack is coming from. Okay, so mitigation strategies. As I mentioned earlier, it's very important to know how much a minute or an hour costs to the business, because from there you can figure out what you want to do. Because in many cases, mitigating yourself on site is extremely expensive. This is a numbers game. So this is why we have providers like Akamai, Prolexic, which were purchased by Akamai, Fastly, Cloudflare, and DDoS Arrest, and a bunch of other companies that basically monetize by aggregating all this together. So looking at the risk pyramid, if you have low level of defenses, is the cursor going through? I think it should be going through, but I'm just checking. You have low level of defenses, and then the lower the level of defenses you have is you have more people that can actually reach this intensity of attack, this level of attack. So there are more attackers that can take you down. Now, if you put resources, the bar is going to go up, which is going to effectively limit the number of people that can execute such an attack. Now, if you go very high, then there will be very limited number of people, theoretically none, but we know that there's never 100% in real life that can execute that attack, but then you will be overspending on defenses. So this is kind of the business side of this thing. Okay, so mitigation, the approaches, as I mentioned, you can either do it yourself or you can outsource it. Thank you. The outsourcing can basically be on demand or always on. So what are the differences? And then you have the hybrid, which is basically a combination of both of them. So if you have on-premise mitigation, here we have the cloud, which used to be known as the internet. And you have regular users, and they send traffic to the server. Then when the bad guys show up and start sending traffic, this traffic is detected and the mitigation equipment goes in and starts filtering the traffic. Thus, the server theoretically is going to get clean traffic. So this is what you do on site. Now, one of the considerations here is that before you can even mitigate on site, you have to be able to deliver this traffic. Now, traffic is fairly hard to scale, or delivering more traffic is easy to scale. However, adding 10 gigabit circuits to your company's co-location is not as easy, and it's also very expensive. So the problem here is that you're limited by the incoming bandwidth. Yes, you have a mitigation device, super duper mitigation device, but if somebody sends you more bandwidth than your uplink to your mitigation device, then you're toast. So looking at the money here for 10 gigabits, and this is prices from like a couple of years ago, and those vary, but for North America, maybe about 2K per month for 10 gig circuit. Co-location space, here we're talking about small deployment, maybe half a rack, something like this. Power and so on depends. This is kind of an average price per port at the time when I was doing this, when I looked at the prices. So this becomes very expensive. Now, when you add people, it becomes even more expensive. And you certainly have limitations there. So if you don't have very large scale of traffic you're dealing with, it's probably better off to have this thing sent outside of the company and have somebody else that is dedicating entire teams and equipment deal with that. Okay, so with external services, in some cases, the pricing may be based on an attack. Those will be usually the traffic cleaners that would take your traffic when the attack happens, then deliver clean traffic to you when the attack is over. They're going to stop introducing their BGP announcements and traffic goes back to you. Or you can basically be paying just based on the clean traffic. Now, the operating model, and this is going to be the case for CDNs, and we'll look at in a second how this thing works. The operating model can be on demand, so attack happens, they take over, or it can always be on. So let's look at on-demand protection. Again, we have the internet here, we have the legitimate users, and then we have the attackers. Once the attackers start sending attack traffic, it gets detected. The detection system is then going to signal the service provider, and then the service provider is going to start injecting BGP routes, which is going to draw all the traffic there, including the attack traffic. Okay, so all this traffic is going to those mitigation pods, but now we have to deliver it in some way to the server. Well, that's tough, right? What are we going to do? We can either do a dedicated server, or as most people do, 99% of the people do, it's going to be a GRE tunnel. Well, the problem with GRE tunnels is that it is going to introduce an additional header. So if I already have packets that are, let's say, at MTU 1500, and they're full packets, and I introduce this header, then I'm certainly going to start fragmenting those additionally, which will have to be reassembled here, which means also there'll be some more bandwidth here. But again, this is a consideration. It's not a deal breaker. Yes. And somebody mentioned here in the chat that it's better to have an external service because more geolocation. Yes, here as you can see, I have only drawn 2 pods, which basically are closer to the users. But in reality, what happens is that they have 30 to 40 and so on. So they will be very close to the users. which in turn is also going to improve some other properties of the connection. And I'll cover this in the CDN side. So anyway, you have those GRE tunnels, which are problematic long-term, because also somebody here may see a GRE tunnel with no traffic when there's no attacks, and then they may decide to clean up the configuration of the router. And what happens next? Well, we have an attack, and the GRE tunnel is not configured on this side because somebody was wise enough to clean up the configuration because the GRE endpoint was not used. So there are a lot of things that can go wrong here. Now, there's also another consideration, the timing of the attack. So we have detection first here. Then after the detection, usually it will have to be a human being that will be paged, that will have to decide if they want to authorize this. I think a lot of businesses are risk averse and they don't do the automatic redirection. But just paging and then sending the signaling, even if we say that the human makes a 1 second decision, we're still looking at a lot of time. Then the BGP route propagation is also going to take some time. So here we're looking at least 5, maybe 10 minutes for this defense to actually start working and effectively cleaning traffic up. So this is, if the attack ramps up very quickly, this is going to be outage time, which you have to be willing to accept. Now with always on mitigation, it can basically be just the second stage of this. We have the mitigation provider with the backend sent here, and whenever the attack happens, they just filter the traffic and so on. Now, one thing I forgot to mention is that in the on-demand type of attack or mitigation, I apologize, if the attacker decides to run several trace routes, they will be able to locate where the origin servers are, which means that when this IP space is moved, they will no longer be able to directly attack the IP space of the server. However, they will still be able to send volumetric attacks against the supporting infrastructure, which is going to be 2 to 3 traceroute hops before the space that was moved away. Thus, if an attacker really knows what they're doing, they can directly attack the infrastructure and the pipes without attacking the space that was already moved somewhere else. Okay, so always on, basically the same picture, but everything's already set up from the beginning. And this also allows you to conceal the location of the origin server. Now, hybrid, oops, 1 second, what happened here? I apologize, I clicked through the slides too quickly. So this was the always on now. Now the next one we're going to cover is actually CDN. So CDN is a form of always on. However, the CDN's primary purpose is actually accelerating access to content. So what happens is you have all those nodes that are forward deployed that will cache some of the content. This is particularly, this is going to be basically the static content like images and so on. And in some cases can cache some of the dynamic content. And in some CDNs, you can also run active processes on those nodes that can actually generate content. Those usually come in as WebAssembly type of plugins that you can run on the actual node. So the idea of the CDN is that they move this front that the customers are facing or accessing very close to the customer. So, for example, like think about Los Angeles, and if my origin servers are in the Bay Area, well, here we're looking at 5 milliseconds latency. What if my servers are on the East Coast? Well, here we're looking at 60 milliseconds latency. So for a three-way handshake to happen, I'm looking at 180 milliseconds. And then for this window that allows me to send larger packets of larger amounts of data before I get an acknowledgement, it will take multiple round trips for this window to grow up. Now, if I was to have a pop in Los Angeles, then the round trip time there would be 1 to 2 milliseconds for every client. The three-way handshake is going to close sub 5 milliseconds. And then from there, all the content is going to be downloaded very quickly here over this connection, which is also going to allow for rapid growth of the window. But even if the window is not growing, I have 1 to 2 milliseconds delay. This is not really an issue. So the content will be delivered much faster to this end node. Now, if there's any content that is not here and needs to be retrieved from the origin server, there's already a backhaul connection that's open, and it already has a large window built up because this connection has been open for a while. And the packet, the object basically will be transferred in one hit. There will be one request coming in here, then all the content is going to be going back on the connection before this thing even needs to send another ACK packet to acknowledge that the traffic is in. It's going to come very quickly. So this is how CDNs work. Now, as a side effect, they also can manage denial of service attacks because they are the front end of your servers. So if somebody is attacking you, they're actually attacking the CDN. And in many cases, basically, it's the CDN's problem. And they're professionals in doing this type of work, so they can defend you fairly well, which is cool. In some cases, they may charge you extra. In some cases, they may not charge you extra. It depends on how often you're attacked and so on. So that, I would say, is probably one of the most successful way of dealing with attacks and mitigating and having a strategy overall for most companies that are like medium and small size. Yep, so that's it on the mitigation. Hybrid basically works as you have a mitigation device on premise. When the device detects that the attack goes above certain threshold, then it is going to signal the cloud to start introducing BGP routes and move the traffic somewhere else. And this, I think, mostly came because of particular vendors that were hardware vendors. Then they were figured out that the cloud is going to pretty much take over their business, and they had to move in that space, but they still wanted to continue selling hardware, and this is how we ended up there. Okay, I'm just checking what's in the Discord. Okay, that's probably not a question for me. Okay. Okay, and this is kind of a quick comparison of the different options we have. Questions? Okay, well, thank you, everyone. If you have any questions, you have my email. And actually, what I'm going to do, I'm going to quickly go to that slide if somebody didn't copy it. So yeah, just put in the subject Django so that I know where it's coming from. And that's it. Thank you very much.